Okay, welcome to heat transfer problem 785, parts A and B. In this case we have a spherical thermocouple and we're trying to measure the exhaust gas temperature. This is what we're looking to find. We're told what this V is, that it's 5 meters per second. We're told that the diameter of this is 1 millimeter. And so we're looking for a couple pieces. Initially at part A, we're looking for the time to get to 2% of the initial temperature difference. And then we're also looking for the emissivity. So we're assuming first that we don't have any radiation, then we come back and look at radiation, how much of an impact that would have on this situation. So what are our knowns? Velocity of exhaust gases, diameter of the thermocouple, and we know the combustor temperature. Where did I lose the combustor temperature to? Oh, that's in the part B. We're looking for find for A time to 98% difference, or recover to that point, 2% of the initial difference. That makes sense. If it was initially 1,000 degrees between this thermocouple and this exhaust gases, we would want to go until we got to 998 or 980. Excuse me, not 998. And we also know we also want to find the effect steady state temp with radiation. That's what we're going to look at. So our schematic, we basically got this guy here, right? We've got some Q by convection. We have some Q radiation. We know the diameter there, this combustor wall is 400 Kelvin. These exhaust gases, when we get to part B, is going to be 1,000. So there you have it. So some assumptions. One, lumped capacitance method is valid. So we're just going to treat that as one fixed temperature. 2, we're going to assume constant properties. 3, say no conduction on through leads. So these little wires are not conducting significant heat out to change our temperature at the junction. And we're going to assume that we have radiation active in part B. Alright, so we have our thermocouple properties given to us. That's in the problem statement. So we have K, it's 100 watts per meter Kelvin. C is 385 joule per kilogram Kelvin. And density is 8920 kilogram per meter cubed. And the combustion gases, this is for the TC. For the gases, we have K equals 0.05 watts per meter Kelvin. Nu 50 times 10 to the negative 6 meters squared per second. And Prandtl number 0.69. Alright. So what do we have going on here? So our analysis. So we know we're going to use from chapter 5. We have the time to reach some temperature difference is going to be rho times the volume times the specific heat. That amount of energy over h bar A of that area times the natural log of this temperature difference, Ti minus T infinity over T minus T infinity. And if we simplify that down, we fill in what V is compared to area. We're going to get some pi's that will cancel out and whatnot. So we're going to get D rho C over 6h bar for a sphere. Ln of 50 for when this temperature difference is 98% of our initial. Alright, so we're going to have, this would be 100 on the top, 2 on the bottom. When that reaches that point, that gets us 50. Alright, so when we look at some correlations, we need to go back and find. Now we need to know what h bar for the sphere is. And if we look in the book, we find the Whittaker correlation. And for that, that's Nusselt for the sphere, the average. Again, that's h bar d over k. That's going to give us something like 2 plus 0.4 Reynolds to the 1/2 plus 0.06 Reynolds to the 2/3 times Prandtl to the 0.4. We're getting rid of that viscosity, the mu over mu s bit, because we don't have anything about mu in this problem. And it should get us pretty close to 1 anyway. What's our Reynolds number? It's going to be velocity times the diameter over nu. So we get 5 meters per second. Our diameter is 0.001. It's looking pretty small so far. Nu, though, is 50 times 10 to the negative 6. So we're going to get something at 100. So pretty slow. Is that we should go back and verify that our correlation here is sufficient with Reynolds number of 100. So as we look at that, rearranging this, so our Nusselt number is going to be 2 plus 0.4 times 100 to the 1/2 plus 0.06 100 to the 2/3 times what's our Prandtl number, 0.69 to the 0.4. So our Nusselt number there, plug that in my calculator quick. 100 to the 0.06 plus times 0.69 to the 0.4. So I get 2 plus 6.155. And then I need to multiply that by k to find h bar. So k was times 0.05 and d is 0.001. So h bar, I think I went the wrong way with this. I must have made a mistake in my calculator with with this calculation. I'm going to get rid of that. If I plug that all in, let me rearrange this. H bar is going to be Nusselt times K over D. So I'm going to have that guy times K was 0.05, D is 0.001. I fill those values in hopefully correctly. I get 328 watt per meter squared Kelvin. So looking back at BO number just to verify that we can do it, it's going to be H bar R of the outside over 3 times K. So we get 328 times 0.0005 over 3 times 0.05. That takes us to 5.5 times 10 to the negative 4. So valid. So that's good. Now going back to our original time bit here, this guy. What do we get with that? So diameter times rho times C over 6 H bar ln of 50. So we get 0.001 times our density for that guy was 8920, I believe. Yep, 8920 up here. Times C is 385. All over 6 times 328, natural log of 50, t, to get to that point, gets us 6.83 seconds. Alright, so that was part A. Now for part B, we're looking for with energy balance. So we're looking for the steady state temperature. So what do we have there? We have Q convection, what it's gaining. Going to equal what is losing by radiation. We're assuming this is epsilon is 0.5 for our 0.5 for our radiation. So we have H bar AS T infinity minus T. So it's coming to the surface equals epsilon AS Stefan-Boltzmann constant times T to the fourth minus T what do I want to call that? The wall temperature. Let's call that TW to the fourth. So as we look at this guy, right, what are we looking for? We can rearrange this. Our areas are going to cancel out. We're going to have to do something kind of guess and check here for a bit. But we're going to find that 1000 minus T equals epsilon over H bar times T minus 400. So we're going to do some guess and check. So let's maybe guess 900 first. T 900 Kelvin. What do I get? I get 100 on this side. Epsilon was 0.5 times 5.67 e negative 8 divided by 328 times 900 to the fourth minus 400 to the fourth. I screwed that up. Alright, so 900 to the fourth minus 400 to the fourth times 0.5 times 5.67 E8 negative divided by 328. I got 54.49. So I think I need to be a little hotter than that. Alright, if I guess that, let's guess T is 950 Kelvin. Alright, so let's try 950 Kelvin. So we have 950, so we're going to get 50 on the left-hand side. The other side is 950 to the fourth minus 400 to the fourth times 0.5 times 5.67 e negative 8 divided by 328. I must have screwed that up. 950 to the fourth minus 400 to the fourth times 0.5 times 5.67 E8 divided by 328. I got 68.18. So now this side is too small, so it must be something less than this. If we keep doing this, we find that T equals 936 Kelvin, or thereabouts. So we're going to run a little colder than our actual gas temperature when we have that thermocouple exposed to the cold wall. And one might ask, how are we maintaining this at 400 Kelvin? Well, maybe there's other heat transfers leaving there. Maybe that's why it's 400 Kelvin there. Maybe we have to cool that with some water wall or something of that sort. So when we do that energy balance, we have to do a little guess and check, because this radiation piece is a temperature to the fourth rather than a direct temperature measurement. So hopefully this was a helpful problem. A couple things just to note. We're using the lumped capacitance method again, even though it was from chapter 5. So this bit here was from lumped capacitance method, using H bar for a sphere. This is what we're doing in chapter 7. And then we're doing this a little bit of radiation back from chapter 1 and 2 type of things. So I hope that was helpful for you as you work on your homework, and we'll see you again soon.